We want to prove epsilon of h tends to 0 as h tends to 0. The method is that we will cut. So epsilon of h is infinite sum, but we'll cut it. So divide into main term and remaining term. So epsilon of h will be sum of a of h plus b of h. In such a way that the remaining term b of h will be uniformly small. On the whole disk of so inside K0 R. So explicitly we write A of H. So namely we can do the following. We can, so for a given epsilon, choose n such that the remaining term, so sum sorry. It's not about the remaining term. I can just use the fact that the convergence is absolute. So sum n equal n plus 1 to infinity n is less than epsilon over 4. So this choice of n is possible because convergence is absolute for the derivative, for potential derivative, and this n allows to divide epsilon into a and b. That's what we'll do. So put a of h to be the sum of the first n, capital N terms, and b of h is the rest. So this is a finite sum. So the actual estimate the important part of the estimate is on A of h, because B of h can be estimated uniformly. Namely, there's a useful formula. So let's rewrite this. So you know the formula for short multiplication, like a squared minus b squared is a minus b times a plus b, right? Do you know the rest of them, the next ones? So the next one is a cubed minus b cubed. So it's just symbolic for any a and b letters. Is a minus b a squared plus ab plus b squared. And so on. Do you know the main, the general formula? I'll write it. So for any expressions a and b, a to the n minus b to the n is a minus b times a n minus 1 plus a n minus 2b. So powers of a go down and powers of b grow, plus a b to n minus 2 plus b to n minus 1. Do you know this formula? Even if you don't, you can prove it by induction. I don't plan to prove it, but we will apply it to this expression. So what we'll get is so it's sum. So the difference will be just h. And then this bracket will be, I mean, I can take h outside, sum z naught plus h to n minus k times z naught to k minus 1. The total sum should be n minus 1. Now, if we divide additionally by h, I'm just rewriting. And then we can erase this h. And this is the useful formula. Good, so I won't need the geometric picture anymore. So then we can estimate so there are two terms, and so let's start estimating the remainder term. So absolute value of b of h is less or equal to sum So now let's substitute here the expression which we used. So less or equal. So now, even though I erased this picture, both of these expressions are bounded from above by R, because we are inside the circle. This is less or equal than R. This is less or equal than R. And this, of course, is less or equal than R. So then this whole thing is less or equal than so putting these together, we'll get R to n minus 1, and the number of summoneds is n. So n R n minus 1. And these also are estimated by now we chose our cutting parameter n such that such sum would be less or equal than epsilon over 4. And we're having this sum twice. And then this is less or equal than twice. So we have uniformly, independently of h, estimated the remaining term by epsilon over 2. It's very small. Now the actual term is just a finite sum. So a of h now is a function. Well, we have the formula for. So now this is a function in h. Z naught is fixed. It's a finite polynomial function in h. So it's polynomial. So the way it's written, it's not clear, but we already calculated that this h cancels out. And the previous calculation shows that for h equal to 0, so let's denote this summoned by 1. So 1 estimated at 0. Sorry for this stupid expression, but let's take a look what happens. If h is 0, I mean, not here, but in the rewritten expression, in this one. If h is 0, then we just collect n copies of z node to n minus 1. But there's second part which exactly cancels this. So 2 of 0 is also n z node n minus 1 because it's just a constant expression. So a of 0 is 0. But well, polynomial function is continuous at least. So there exists h whatever, I don't know, h node for absolute value of h less than h node, absolute value of a of h is less than epsilon over 2. So then in total, absolute value of epsilon of h is less or equal than absolute value of a of h plus absolute value of b of h, which is estimated by epsilon over 2 plus epsilon over 2, which is epsilon. So I proved that the limit for h tending to 0 epsilon of h is 0. So then thus f of z, which was defined as sum is differentiable at z node with f prime of z being the sum n equals 1 to infinity n a n z node to n minus 1. So that's what we wanted. This is the end of the proof of the theorem. It was quite cumbersome, but the main idea is that you have some infinite expression and part of it behaves like a normal polynomial function, and the remaining part can be made really, really small. Good. So the theorem is proved. Corollary. So if rho is radius of convergence of sum a n z to the n, and f of z is given by the sum, then f prime of z obtained by term-wise differentiating series is also holomorphic, also differentiable at any point in the disk of convergence, because we proved it for any function obtained by sum of series, and this is also sum of series. Right? So we get something. So remark, this looks very different from real analysis. Right? So in real analysis, there are functions which can be differentiated only once or twice or finite number of times. Here, if a function which is obtained as sum of series is differentiated once, then it's differentiated as many times as you want. So another corollary maybe I'll just ask the question and the answer will appear immediately. So f of z is sum of series the question is how to recover coefficients from the function f. Well, let's start slowly. What's a0? a0, of course, is the value of the function f at 0. Because if we sum an 0 to the n, we'll get a0. But what's a1? We can differentiate f and evaluate at 0. So then we'll get exactly a1. I would rather write 1 times a1. What's a2? If we take a function and differentiate it twice, so the exponents will be shifted by 2, and what was at the place 2 will end up in the place 0, but with coefficient changed by, differentiating twice. So 1 times 2 times a2 is f double prime at 0. Now you see the pattern. N factorial an is f differentiated n times, and we're allowed, in view of the previous corollary, evaluate it at 0. So so the answer then is an is f differentiated n times, evaluated at 0, divided by n factorial. So in particular, if somewhere around 0, 2 series an z to the n and converge absolutely in some k0r in some disk, then converge to the same function, to the same f of z, it follows that all coefficients are the same. So you can recover this series completely from the function. Good. Now let's talk about the basic example of holomorphic function apart from polynomials, which is exponential function. Can you please turn the camera? So definition, exponential series sum n equals 0 to infinity z to the n divided by n factorial, where 0 factorial equals 1 just by definition. So now looking at coefficients, we see that, well, for every t, So factorial grows very fast. Factorial grows faster than any power. So for any t to the n by n factorial is bounded, so the limit is 0. It follows that the radius of convergence equals infinity. So thus the sum denoted by exponential function of z is holomorphic everywhere on complex plane. So it converges, and so is holomorphic. Now we remember that holomorphic functions, which are sum of series, can be differentiated by term-wise differentiation, and this series is special. Z to the n over n factorial prime is z n minus 1 over n minus 1 factorial, which means that no matter how many times you differentiate exponential function defined like this, you get the original function. Now from this you can derive the key property of exponential function. We'll see that these, well, this is one incarnation of this key property, but another incarnation is that it's multiplicative. So we didn't write that exponential function at 0 certainly equals to 1, but this is clear from the beginning term. Now let's prove this. So consider a function, call it f of z, which is exponential function of z times exponential function of some constant minus z. So later we'll choose a constant. So it's a product of two holomorphic functions. It's holomorphic. Let's find its derivative. Now its derivative is, so we do it by Leibniz rule. Well, and then using the chain rule, so it's 0. So the derivative vanishes. Now from this it follows that all partial derivatives vanish, so this function is simply constant. So it's enough to find its value for some particular value of z. So then f of z equals f of 0 is exponential of c for any c. Now, where should I continue? Maybe. So take c equal z plus u, then we'll get that exponential function of z times exponential function of u, and this is z plus u minus z, is exponential function of c, which is exponential function of z plus u. So we can erase the middle, and we see the key property we wanted to prove. So for every two complex numbers, we'll get this. So definition, the value at 1 is called e. It's the usual expression. Then exponential function at n is exponential function of 1 plus 1 n times. So then it's e to the n. And in the same way, then you prove that exponential function of any rational number is e to the power p over q, which is so we get the usual exponential function. So exponential function of z restricted to real numbers is the usual e to the x. I mean, you check by continuosity and then. Good. So yeah, there are things to remember about exponential function. So things to remember. About there are three things. And the last thing is the additivity. Good. Now, using this, we can talk about trigonometric functions. And again, talking about trigonometric functions starts from series, and series are the well-known one. So we can consider sum from n equals 0 to infinity minus 1 to the n z to 2n plus 1 to n plus 1 factorial. And this is sine of z. And cosine of z is sum n equals 0 to infinity minus 1 to the n z to 2n over 2n factorial. So again, since denominators grow so fast, they converge everywhere on complex numbers and are holomorphic then. Converge absolutely. Now comparing coefficients. Of this series, so what's the difference between exponential series and this series? There are two differences. Here are only odd powers. Here are there only even powers, and also signs switch. Right? In exponential series, there's no switch of the signs. So how to express one via the other? So lemma, and the proof is by comparison of coefficients. So as series, and so as function. In Z. So when I say as series, this means just comparison of coefficients. But we know that the sum is uniquely defined by these coefficients. So we have that exponential function of z is cosine of z plus I sine of z. Only of Iz. So we need to make coefficients switch, like change signs, and for this we put I here, and then so we'll get this. So I mean, coefficients here will be of the form I to the n over n factorial. But then depending on parity of n, well, actually not on parity, on n mod 4, I to the n over n factorial is, so if n is 0 mod 4, then it's 1 over n factorial. If n is 1 mod 4, then it's I over n factorial. If it is 2 mod 4, then it's minus 1 over n factorial. And if it is 3 mod 4, then it's minus I over n factorial. So then it's clear that these two contribute to cosine, these two contribute to I sine. So we get both the switching of the signs and we divide the whole sum into two groups. Good. So this is the main trigonometric formula you can imagine, because from it you get all possible expressions, all trigonometric equalities you are supposed to know from your high school life. So let me try prove one of them, and then the rest of them are proved exactly in the same way. So I don't know how you proved it in high school, but this is the correct way to do it. So we know that exponential function is additive. Now let's rewrite both of them, and then we'll get, so this thing is cosine of z1 plus z2 plus I sine z1 plus z2, and this thing is cosine z1 plus I sine z1 cosine z2 plus I sine z2. And now we know that these two numbers or functions coincide. You can take z1 and z2 real, for example, then this will be the real part and the complex part, I mean the imaginary part of this function. So then it would be enough to compare real part and imaginary part. So then we'll get, in the left hand side we have cosine of z1 plus z2, and in the right hand side, I mean and this will be z1 z2 are real, and this will be cosine z1 cosine z2 minus sine z1 sine z2. It's just complex multiplication, and in the same way imaginary part of left hand side is sine z1 plus z2 is imaginary part of the right hand side, and this is cosine z1 sine z2 plus sine z1 cosine z2. So believe me, this is the main trigonometric formula, and the rest of them follows from this one. So I don't know how you were taught in high school, but actually at some point I taught students using Stewart Book of Calculus, which probably is yours as well, no? No? You're lucky, because on the back page of that book there are 17 trigonometric formulas, 17. And poor students just remember them one by one, but in fact you need maybe 2. So this is one of them, and the other is about cosine squared plus sine squared equal to 1. Good. So are there any questions? I covered the first 5 sections of first chapter. So and